Begin.
Thank you very much. My name is Piepmeier from NASA Goddard, and I've been working in radiometer technology and spaceflight radiometers for nearly 2 decades now, and we are just finished up this 2-year ACT project on array-fed radiometers. And I'd like to recognize my industry partners, Jared Jordan and Will Stacy from Cubic Nubitronics, and the Goddard team led by Science PI Thomas Holmes. Next chart, please. The science motivation for this project came from Thomas Holmes desiring to measure land surface temperature under all weather conditions using 37 gigahertz. But the application is actually quite broad, and to nearly all measurements that microwave radiometers have done for the last about 4 decades of land, ocean, ice, and atmosphere. And there's an interesting engineering and challenging engineering problem on how to maximize spatial resolution, which turns into aperture size, while optimizing beam efficiency, spatial sampling, while trying to operate in multiple bands over nearly a decade of frequency, say from 10 to 100 gigahertz. And what happens is that this optimization usually leads to accepting edge-to-edge 3D contour sampling, as seen in the left. That's the GPM microwave imager on the GPM satellite, and on the ground is just a notional edge-to-edge sampling shown with the two blue ellipses there. And this leads to undersampling, spatial undersampling the scene, which can lead to aliasing if the scene is complex. So on the right, I show 2 examples showing the difference between undersampling and Nyquist sampling. The top panel shows the improvement that one can get imaging ocean convective storm cells. In this case here, we took the 166 channel from GMI and modeled convective storm cells and shows the undersampled imagery. And then Joe Munchak, who did this work, reduced the aperture size in his model to half meter and did Nyquist sampling, and found that the convective cells are much better resolved and can get a more accurate measurement of the depressed brightness temperature for light scattering. And similarly, in the bottom panel, we show 37 gigahertz from a notional 2-meter system, like perhaps one of the Answer 2 radiometers. And again here, because of the antenna optimization, the imagery is undersampled, and we find that when we Nyquist sample, in fact, we discover that the undersampling or the aliasing was obscuring the morphology of the water body. Next chart, please. Okay, so I'm going to describe how the proposed solution was arrived at and how it works here. And I'm going to pick on the GPM microwave imager again. The engineers at Ball Aerospace did a fantastic job optimizing the antenna design, having to operate from 10 to 200 gigahertz. But because of this, they had to give up Nyquist sampling at the higher frequencies. So if I start at the left, this shows 2 consecutive scans of the GMI footprints on the ground. Good footprint overlap, which leads to Nyquist sampling. But as we go higher in frequency, all the way up to 90 gigahertz, there's actually a gap. And in fact, to try to close this gap, the antenna design under-illuminates the reflector to try to increase the beam width. So you can see this in the second panel. If we were to fully use the aperture to its full diffraction limit, we'd have finer spatial resolution at the high frequencies, but larger gaps. So to solve this, one would need to add more beams, as we can see in the third panel there. But this actually isn't possible because of needing to have multiple feed horns in this big feed farm, and adding more feed horns requires pushing the feeds further off focus, and if you get pushed too far off focus, your beam quality degrades, and you can't meet requirements. So this is why the GMI approach is a exquisitely balanced design, balancing all the different requirements. But what if, moving all the way to the right, what if we could overlap all these different speeds all as close to the focal point as we can bring? Which brings us to the next chart. So often in Earth science, we look at what the radio astronomers have been doing, because they tend to lead the way in technology, because they don't have to put things into space. And over the last decade, the community, the radio astronomy community, has made excellent strides in developing focal plane array feeds for their telescopes to address the problems of needing multiple beams, doing beam steering, beam shaping, or side lobe nulling out radio frequency interference. And on the right are some examples, and on the bottom right is an L-band dipole array that's operational for observation campaigns at the Green Bank telescope. So with this idea, next chart please. So with this idea, we worked with Cubic Nematronics and their polystrata technology to develop a decade bandwidth of through W bands of all the focal plane array. And Jared and Will designed this 8x9 array that operates from 10.6 gigahertz to 92 gigahertz, covering all the radiometer imager bands. It's made of 17 cards with polystrata, so it's essentially all copper. You can see two of the cards in the upper middle picture that were used in a transmission test. The complete array is shown from several different perspectives on the right, and the array has beam combiners to form line elements in there. We verified the operation of this array using a near field antenna range to collect the individual line patterns, and then in data analysis did conventional planar array beam forming and beam steering to scan the beam router-related software. And there was excellent agreement between simulation and measurement. So this is the widest bandwidth array that certainly we've developed at Goddard, and Cubic Nematronics has developed, and developed some good technologies to remove connectors, assembly processes to operate over this bandwidth at these frequencies. Next chart, please. So in parallel, at Goddard, while Nematronics was developing the extra W band array, we wanted to do a technology demonstration to push the TRL a little bit higher, since we're working in the low TRL technology. And so we performed a laboratory demonstration to demonstrate the idea of generating multiple overlapping beams so we could fully nyquist the scene. We did this at 36.5 gigahertz using an array, a line array that Nematronics fabricated based on a previous program. You can see this array in the upper left panel. The little square box is the array, and that's feeding an 80-centimeter aluminum reflector. We put this on the contrast range at Goddard and collected the intermittent frequency signals with a radar receiver that we repurposed as a data acquisition system. Chart, please. And the results were very exciting. And Paul's going to hit play. So we used the maximum signal-to-noise ratio beamformer technique that was developed for radio astronomy. That balances main beam gain and noise created by spillover. We would probably use a different technique for Earth science, maximizing beam efficiency. But nonetheless, on the near field, on the contact range, we scanned the antenna patterns of all the individual elements, 0.1-degree steps, to map out the half-degree main beam and recorded those IF signals. And software, we just use the software correlator to compute the covariance matrix. And then Using those data, where we use the max SNR beamformer to compute weights, so it's adaptive. And then each beam is simultaneously created by combining the weights with the covariance matrix. And this is done all in post-processing. And you can see from the weights that we're actually moving the phase center of the beam as opposed to moving the phase taper of the beam to and steer the main beam out of the reflector. And next, final chart. You can get out of the animation. Yeah, great. So to wrap up, we've made an initial TRL advancement demonstrating the capability of creating a wideband array feed and then using a wideband feed to generate multiple overlaps with the main reflector. We're really pleased with these results, and this has motivated us to pursue to integrating active devices